Today, we're going to be talking about universal quantum computers. So last time we talked about how the evolution of any quantum system can ultimately be described by a unitary. It might be that that unitary acts on a larger system that you have access to. Maybe you should think of the unitary as acting on your system and some environment degrees of freedom. But the fact that any evolution of any quantum system can ultimately be described using a unitary is motivation for us to just ask, well, which kinds of unitaries can we implement? So that's really the focus of the lecture. Now, okay, which kinds of unitaries do we care about? So evolution of any pure quantum system is under some unitary matrix. If we have n qubits, for example, then U is some 2 to the n by 2 to the n matrix. An example of a unitary that we might want to implement, particularly those of us coming from physics and chemistry backgrounds, is evolution under a Hamiltonian that we care about, okay? So let's imagine that we have some complicated molecule or condensed matter system that we believe is described by some Hamiltonian H. Then the evolution will look something like this, okay? So let's say we know H because we have some guess as to what the Hamiltonian is supposed to be based on our experiments. And our aim now is to construct some simulation of that system or the simulation of the model of our system. How do we implement this thing? So, so what this lecture is going to be about is how you can implement any unitary using very simple local operations. So this is analogous to the fact that your computer is ultimately just running on simple logic gates, right? It's a bunch of transistors that somehow implements very complicated functions. This lecture is essentially about this, okay? Now, that sounds a little bit dry, but there's actually quite a lot at stake in this, right? So, and this comes back to this idea of the so-called extended quantum extended Church-Turing hypothesis from Deutsch in the 80s. So let me just remind you of at least, a statement of the Church-Turing hypothesis from classical computation. So the statement it sounds very mystical, right? Every finitely realizable physical system can be perfectly simulated by a universal model computing machine operating by finite means, okay? So the basic idea is that any physical system, anything that happens, should be describable using a computer, right? So there are some issues that you run into actually when you apply that idea in the classical setting, in that you're working with a Turing machine, some operation on binary degrees of freedom, and maybe you're trying to describe some classical mechanical system which has continuous degrees of freedom. So you run into some problems. So Deutsch's idea from the 80s was basically to see if you can reformulate this idea in the quantum setting. Okay, so in the quantum setting, the question then is, okay, well, if the idea is roughly the things that happen in nature are just unitaries, they're just Hamiltonian evolution. So the kinds of unitaries that can happen, that can occur naturally, should be the ones that we can implement using a kind of quantum computer. Okay. So the idea is that anything that happens, we should be able to describe using elementary operations. Okay. Another way of saying that is if there is no simple way to implement some big unitary, it probably doesn't happen in a reasonable amount of time. So this is basically a question of like, can you use a quantum computer to simulate like a real physical system exactly? Okay. So another thing I want to flag here is why you might want to try and use a quantum computer for this task in the first place, okay? So, of course, a classical computer is able to store some matrices of up to some fairly small value n, and you could ask, well, why can't I just make a very big computer, or a very big classical computer that can take some quantum state I care about and evolve it under a unitary? So, for now, I just want to give you a sort of sense of scale about how much of a disaster this is and why it's so essential that we build quantum computers for describing the evolution of many body systems. So I did a little calculation to basically figure out how much money it costs to store a wave function of n qubits, right? So let's say you have n qubits, n qubits, and you're allowed to have, and you want to know, okay, what is the n I can afford? So okay, let's imagine that you're really very wealthy, and you have $1 trillion. So if you have $1 trillion, I want to ask how many qubits can you represent the wave function? So it costs about $10 per terabyte. Okay, and then if we wanted to store a generic quantum state in double precision, so that's 2 to the 6 bits per component. So double precision means we have 2 to the 6 bits for actually 2 to the 6, because we want both the real and the complex part, real and the imaginary part. It's 2 to the 7 bits per component. And there's 2 to the n components. So with $1 trillion, it turns out that gives you a 72 qubit wave function, okay, which is not very large, right? Ultimately, we're interested in describing large molecules, or we're interested in describing condensed matter systems where n is the order of Avogadro is constant, and 72 is pretty small, right? So it's basically just impossible to describe many-body quantum systems using classical computers once n gets sufficiently large. And that's really the motivation for working with a quantum computer, where with n qubits, you naturally represent the state of an n qubit system. Right. So now with that motivation there, let's ask which unitaries we can implement. So we're going to use a gate-based model, right? So when we use it, what I mean by a gate-based model is I'm going to want to build U out of so-called elementary operations. So let's draw our qubits as like lines. This is a circuit. And this is time. Okay? So each of these is a qubit starting in some state. And the kinds of elementary operations I want to think about are the ones that couple pairs of qubits or act on individual qubits. So one example of an operation would be this. Okay, so that's a single qubit unitary acting on one of the qubits. Another kind of operation I might be interested in is a swap gate. Okay, so a swap gate basically does this. It just exchanges these qubits. I'm not going to draw it that way in a moment, but that's the idea of what the swap gate does. Another kind of operation that's going to turn out to be absolutely key today is the so-called CNOT gate. Okay, so CNOT is going to be the kind of main character in today's talk, and I'm going to be talking about how you can basically build almost anything you'd be interested in out of a CNOT and these single qubit gates. I should say basically, I mean literally everything. So I'm going to show you how any unitary on n qubits can be implemented just using CNOTs. Okay, also swaps, but swaps you can build from CNOTs, and also single qubit unitaries. Okay, let me just say that again. So today, any U from CNOT plus single qubit U. And now you call this a universal gate set. So this is the analog of saying that basically you can implement any classical computation on a bunch of bits using simple operations like AND, or I think NAND is supposed to be universal, but don't quote me on that. The analog of that is CNOT and single qubit gates. We'll talk about another universal gate set later. And a lot of, but this is the kind of first one, to my understanding, that was studied in a lot of detail. So what we're going to do is kind of go on a whirlwind tour that's hopefully less technical than, but hopefully more readable than, a paper from Barenco and co. So if you want a kind of more technical version of what we discussed today, it's going to be Barenco et al. Physical Review A. And the reference is 523457 from 1995. So, okay, let me explain what that CNOT gate is. So what CNOT does is it performs so we have a kind of target, which is here. And we have a control here. Now, okay, what CNOT does is really simple. It says if the control is in the state 1, then apply the X operator or the NOT operator. Okay. So CNOT we can think of as if the control is in state 0, let's call it C for control, then we apply identity on the target. And if the control is in state 1, then we apply the X operator on the target. Okay. So X is just flipping 0 to 1 and 1 to 0. And of course, you know, when I've said how it operates as a operator when the control qubit is in 0 or 1. Of course, you know, this is a linear operation, right? So this tells you also how it's going to act on states where the control is in a superposition of different states. Okay, so that's what we need to know about CNOT. We also need to know something about single qubit unitaries, which are the other key building block today. So, okay, what is it? So single qubit unitaries have two key properties. So one of them is that you can write them more ways in the following form. So remember, this is just, okay, this is an operation on a qubit, which is a two-level system, and it can be visualized, also the transformation of Pauli matrices, if you like. But the idea is basically this. So let me explain these different operators. So this is a rotation about like the z-axis by delta. This is a rotation about y by gamma. And so if you wanted to think about how this is acting on a single qubit, then what you should do, I'll just draw this on the side and erase it in a moment. But like a single qubit state can be visualized on the block sphere, which many of you will be familiar with. And then the idea is that, okay, well, the state of a qubit corresponds to some like vector in this block sphere. And then this thing here, RZ delta, is going to basically take this qubit and rotate it around the z-axis by delta, okay? So RZ delta takes our qubit from here to here. Okay. So that's all. So all I'm saying here is any single qubit unitary can be written. I mean, this is just some 2x2 matrix, right? And you can check this yourself. Any 2x2 unitary can be written as a product of 3 rotations and then some overall phase. The other property we're going to need of unitaries is the following. It's that by choosing appropriate rotations, you can show that also any unitary can be expressed as this is kind of weird. Okay, A, B, and C are generic. These are X operators. And we want A, B, C to be equal to the identity. Okay, so this is just some other decomposition of unitaries that's going to be really useful for us when we start building more complicated operations. X, Pauli X, A, B, and C, just generic unitaries. The point is they're just constrained to satisfy this condition here. Okay, so what we're going to see is that using these two, we can very quickly and kind of iteratively construct extremely complicated unitary operations. Let me move this out of the way. Over myself. Okay. So now I can sort of I can sketch the kind of outline of what we're going to do. So the ingredients are going to be we're going to take CNOT and single qubit U. Let's call it U1, the single qubit U. We're going to combine these things into things that I'll call like C, N, and NOT, where this is a multi-control operation. So what CN0 does is, it's like a bunch of if statements, right? So C n naught, it's an n qubit controlled knot. So what C n naught does is it says, well, if all of these qubits are in state one, then flip this one, okay? Whereas this was C1 naught. So the approach is going to be to use these things to construct Cn naught and Cu naught, where Cu naught is going to have this form. So what this means is if all these qubits are in state one, then apply U, same sort of notation, another control operation. Having used these CNOTs, the C0 and the U1 to construct these very complicated operations here, we're going to construct something called a two-level unitary. And then from two-level unitaries, I'll explain what these are in a little bit more, in a more concrete way later. But one way of thinking about these things is to say that, well, okay, like a generic unitary is some huge matrix in a 2 to the n by 2 to the n space. A two-level unitary acts non-trivially on just two basis states, right? So you can imagine this thing as like doing nothing to 2 to the n minus 2 of the states, and then it does some unitary rotation in some 2D subspace. And then from these, we'll construct any unitary. So in that sense, C0 and U1 are universal for quantum computation, okay? That means that, okay, you're coming from an experimental background, all you need to do is implement C0 and U1, and you can do literally anything, modular error correction. Like in a noise-free world, these two operations would be enough to implement any operation on an n-qubit system. Okay, so that's the kind of plan for today. At the end, I'll talk about another universal gate set briefly, which is the so-called Clifford plus T. But let's get started on some of these iterative constructions. Before I get going on the iterative constructions, though, it's important for me that you understand these diagrams, because it's going to be all diagrams from here. So I'll stop now for any questions.
The kilobytes that you are those like hard memory, or is it the memory that is used to do the computation, basically the evaluation?
Oh yeah, okay. So over here, I'm just talking about hard memory. I'm just asking, like, let's say I wanted to just for storing the wave function. This is yeah. So okay, actually, so this turns out to be also about the number of not too far off the number of bits we have in the world in all digital storage right now. So it turns out we have about 1 Avogadro of bits globally. And so a little bit more than that, as of, I calculated a year ago, maybe it's more by now. So yeah, so the basic point is that you can't, like wave function, the many-body quantum state almost is not a meaningful description of a system once you get n beyond the scale where you can write it down. But this is really just like if you overwrote everybody's phone, computer, and national lab computing infrastructure in the world, you get to write down 1 qubit, 1 wave function of 72 qubits in double precision complex float.
I fully understand sympathize with this strategy. So I'm curious whether we can try a different direction of exploring this question with like maybe tridiagonal Hamiltonian as your starting point instead of.
Yeah. Okay. So there are actually an enormous number of different models for universal quantum computation. So here I'm just focusing on the one that's explored in enormous detail in this Barenco paper. But mostly, okay, almost for its historical significance, also because it's kind of more straightforward to see what's going on with diagrams. There's a huge body of literature exploring, these other models of universal quantum computation. So in fact, like Barenco and Deutsch have some other papers showing that if you take single qubit unitaries in almost any 2 qubit gate, then that's also universal. So there's a lot of freedom. I don't know the tridiagonal Hamiltonian example myself, but I wouldn't be too surprised if you can do it that way too.
I didn't understand what the CU not does. Why there is the not in the name?
Oh yeah, sorry, you're right. There shouldn't be a not in the name. That's just CU. Yeah, sorry, the CNU.
Okay.
Yeah, okay. Thank you very much for catching that. Okay, that's just the CNU operator. N qubit controlled U. not just means X. So CN not is CNX. Okay, but everybody's happy with the diagrams? Great. Okay, let's start with the iterative constructions. Okay, so yeah, I'm going to go over it. Okay, reading through that Barenco paper will take a long time. So I'm going to give you a sketch of how it all goes. And if there's parts that you want to know about in more detail, then Barenco's got you. So first off, what we're going to do is construct C naught or C2 naught. So so first off, yeah, okay, let's see. So where's my C2 naught? Okay. First off, we'll do CW, C1W, where W is some single qubit unitary. So we just need to build the first few layers, and then everything else is going to be iterative. So to get CW, what we do is the following. This is also hopefully going to give you an idea of just how you build quantum circuits and get you a bit familiar with the notation. Okay, so this is CW, where where W here is W here is, if that's in 1, then what we're going to act with is A, then X, then B, then C. So it's going to be A, X, B, X, C. So okay, I realized my notation is backwards relative to that. So yeah, basically the point is, okay, if this was in state 1, then you can see what's going to happen is we act with A. After acting with A, then we apply the X operator, then we apply the B, then anyway we apply B, and then we apply X again, and then we apply C. So here W is equal to this product, and we also want the identity to be CEA. Okay, so all the notation unfortunately reversed relative to over there. Apologies for that, but you can relabel and you get the same thing out. So now you can see what happens if you put 0 up here. So with a 1, you get W, and with 0, because we know we can construct this stated over here, what we find is we apply A, then we apply nothing, because that's a 0, then a B, then nothing, then C. But we've defined CBA to be this, okay? So that's our control W1. Okay, so next what we need is, let's go for control 2 W1. Okay, so a bit more complicated. So the way this is going to go is it's going to build from this, right? So once we have this, we start constructing these things. And so what we'll do is the following. So we'll have okay. So again, so now it's CNOTs and these constructions up here. So, but now each of these things, remember, is itself this product up here. Okay. So gradually we're going to build more. We're going to just build these huge operations in this way, right? Ultimately building towards this multi-controlled CNOT and multi-controlled U on an arbitrary number of qubits. Okay. So is everybody happy with this part? Okay. Sorry.
No, could you just clarify the notation? So when you say the W, C, X, B, X, A, you mean that X is not a single X, it's actually CNOT?
Oh, no. So this, okay, so, sorry, good question. So what I want to implement is C1W, where this is W acting on a single qubit. And here I'm just going to, I want to be able to implement this for any operation W. Now the point is that any operation W, which is a single qubit operation, can be represented as this product. Sorry, that's probably, sorry, see, this C is not control, that C is that C.
Yeah.
Maybe that's, yeah. So any W can be implemented in this way, where all of these are single qubit unitaries. But I know that I can perform this decomposition in such a way that the three single qubit unitaries appearing product the identity. So the point is that they're using this property. I can implement the control W operation in this way. So my actual implementation of control W involves single qubit unitaries in CNOT, but the W I can do this for any W because W can be constructed in this way. So I think the way of thinking about it is to say, I've got a control W I want to implement for a particular W.
You just write this representation for W, not for the control W.
Yes, exactly. Yeah. So I pick a W, I decompose it in this way, which is convenient to me. And I know this decomposition exists. And then I build a circuit in this way so that I implement the control W operation. Okay. So
How unique is this decomposition? The
Um,
CBA?
let's see. Okay. In the notes, there is a particular unique choice of ABC. There's a choice of ABC you can just like pick straightforwardly. The idea is that like I'm not sure if it's unique, but if I know what U looks like in this form, then there's a choice of ABC that is determined by beta, gamma, and delta that gives you this. Probably there's some freedom in it, but yeah, I don't know for sure. Okay, so that's the base level, and now everything is just going to follow from these two steps. So recall that, of course, I can do this for like CC naught, right? I could just set W to be equal to X, and I have C2 naught. Oh, I should add actually, just for notation and so for your own understanding of the literature, I'll give you an example of this, which is called the Toffoli gate. Or Toffoli, I don't know how to pronounce it. So the Toffoli gate is like C2X. It's this thing. So when people talk about Toffoli, they mean this.
Could you also, what's the plus instead of the X and what's B plus?
Sorry,
In the
plus.
picture of C2W1, instead of you put,
Oh,
like, the circle
yeah,
plus.
no, sorry, they're the same. Sorry, okay, yeah, sorry, no, I don't know why I flipped those around. So the X in the box is the same thing. In fact, people actually usually draw C naught with a plus rather than an X. I realize I mixed it up because I call it CX. I've been calling it CX as well. So just to clarify, plus in the box is the same as cross in the box.
Okay, and then what's, you have V and then V plus and then V.
Oh, that's V dagger. Sorry,
Oh,
that's the
okay.
emission conjugate. Okay, yeah, thanks for the clarifying questions. In fact, let's stop screwing up the notation. All of these should be plus. Okay. So now let's build from this thing and these things, we're now going to build arbitrary multi-qubit controlled knots. Okay, just going back to this kind of Deutsch way of thinking about it, let's just remind ourselves how weird this is. So these constructions are going to get pretty arcane, right? But the funny thing is, of course, if you believe everything is described by quantum mechanics, the point is that everything can just be described using these ridiculous combinations of multi-qubit controlled NOT gates. So it's just going to be let's say, generally inefficient way to do things. Like, of course, if you have a system of interacting electrons, the way they are implementing their own dynamics is not using a bunch of NOT gates. They have another way of doing this. Okay, so maybe the remarkable thing is that you can often simulate these quite physical systems without an enormous overhead using these apparently very unphysical operations. Okay, so now let's do the iterative construction. So let's go for CN naught. I'm going to need one extra qubit for this. As you'll see what I mean by that in a moment. So to clarify here, this qubit's not doing anything, right? This qubit's just hanging around. These are all these things with the circles. These are all the controls. Okay, so the idea is that you can write this thing So here what I'm doing is I'm writing down CN not as 2 CM knots and 2 CN minus M plus 1 knots. And the point is you can do this for any M greater than or equal to 2. Okay. Let's just I think it'd be useful because this is now getting pretty sophisticated. It would be useful to just go through this example to see exactly what's going on here. Okay, let's just ask what's happening when all of the when it acts as expected. Let's see what happens when we put all of these control qubits in the state 1 when they're supposed to perform this bit flip conditional on their states, right? So for example, if these are all in state 1. Then what's supposed to happen is that when they're all in state 1, we apply the X operator, okay? So any state psi should go in here and come out as X psi. So what's going on out here? So let's say we have, okay, these qubits are in state 1. We don't care what this thing is doing, but for simplicity, let's say it's, we can, for simplicity, let's say it's in state phi. And this is just going to come out as phi. And so the same thing should happen here. It doesn't touch this qubit. And we want to see that all of this goes through, right? So phi goes in here, psi goes in here. What happens? Okay, if these 3 are in state 1, then we're going to flip this, okay? So here, we get X phi. Then having done that, we've got X phi on this leg. We now ask, oh, actually, okay, it's going to get really complicated, that's X phi. Let's say that phi is 1 to keep this not too complicated. Okay, phi is just going to be 1 over here. Otherwise, we're going to have to deal with superpositions over multiple operations of the multi-controlled CNOT. And a multi-controlled CNOT is complicated enough, right? So, okay, let's say these are all in 1. So in this case, what's going to happen, if these are in 1, we flip this 1 to a 0, right? It's controlled on these 3. So that 1 becomes 0. Now we look at these 3 and we say, okay, well, we've got a 1 coming in, a 1 coming in, and a 0. Those are not all 1. Because they're not all 1, we're not going to do anything, okay? So here we get we don't act with this operation. And we get psi coming out on this side, right? We do not act with X because that was in state 0. Next step, here, these are all still in state 1. So we're now going to flip this again. So we act with the not here. So what was a 0 comes out as a 1. And then this layer, we now have 1, 1, 1. And so we finally flip. So we get X psi as required, okay? So it's a laborious exercise, but you only need to check it works for the first few values of N and M. And the point is that this, so one CN not can be broken into 4 CNOTs on a lower level. Okay, now with that covered, we can see how a similar, I'll just state how it works for CNU for more general U operations. And you can see how it works by a similar exercise. There's going to be a slight caveat here. So, okay, now that we've gone through that example, and you can, work through this yourselves to convince yourselves. Let me just be clear on the fact that there was no requirement on the inputs over here. There could have been anything, and we would have implemented the CNOT successfully. My erasure of phi earlier was purely pedagogical, or the opposite. So to implement CU not, what we want is this. Okay, so we want to implement a U here. And now what we're going to do is fix this to be 0. And then we'll do that. What we're going to try to implement is this multi-control U. So this multi-control U, with that fixed to 0, it turns out can be expressed in the following way. So it's a single qubit controlled U down here. That's fixed to 0. And then we'll have 2 huge CNOTs controlled on all of these. Okay. So there's our arbitrary controlled U. So this is our iterative construction, starting from these very simple gates of now what look like ridiculous many qubit operations. Okay, so now before we proceed, sorry.
So if you have 0, 1 as your 4 qubits, so implement B.
If I have 0, 1. So you say I put 0, 1 over here.
Yeah,
So it's not supposed to implement W.
yeah.
Now when I do this, I get, okay, so the 1 here is going to give us a V. Then this thing is going to flip 1 to a 0. We've still got a, so, okay, we wanted, sorry, there's a 0, it doesn't do anything. There's no, that stays as a 1. Now we implement V dagger. So the V dagger here is going to now, okay, so we have to do V dagger, so we get V, we get V dagger. Here we still do nothing. So then we implement V. Yeah, you're right. What's going on there?
Square.
Oh, yeah, I'm sorry. Yeah, good catch. I am, thank you for catching that. It's this. Yeah, sorry about that. This controlled V should be on the upper qubit. Thank you. Yeah, I just copied that out of the notes wrong. Okay, so we've seen how to construct some very complicated gates. Let me just comment briefly on how long it actually takes to implement these things. So you'll find a very, very detailed analysis of the implementation costs in terms of elementary operations in Barenco. But here we can just satisfy ourselves with a basic scaling analysis, okay? So the question is, how many elementary operations to get C and not? Basically, what I want to know, and this is what I want to know is how this cost scales. Okay, I don't want the exact cost. I want to know if it costs like n gates, or like n squared gates, or x n gates, for example. Okay, so. This is a pretty important concern if you actually want to implement any of these things in practice. If something costs exponential number of gates, it's a disaster, right? And in fact, there are bad ways to use this iterative construction kind of backwards, which will allow you to decompose the multi-controlled knot into some extremely inefficient object. So what we're instead going to want to do is actually, what's the cheapest way to do this, right? And so we can get an idea of the scaling just from this analysis. Okay, so let's do CN knot. So what we do in this decomposition. So recall that CN knot breaks into 2 CM knots and 2 CN minus M plus 1 knots. So what we'll do for any M greater than or equal to 2, what we'll do is we'll choose M is equal to the floor of N over 2, okay? So the largest integer below N over 2. So what happens then? So what we see is that our CN knot is going to turn into, I draw this as a tree. So CN knot is going to break into 4 times CM around N over 2 knot, okay? So, maybe it's N over 2 or N over 2 plus 1, but we broke it up in this way, right? A given CN knot breaks into 4 CM knots where M is around N over 2. So now we ask, how many times do we have to do this? So the point is that if we do this, let's imagine doing this k times. So after k steps, our CN knot has turned into 4 to the k CM knot, where M is of order n over 2 to the k. Okay, every time we do this, we break down the size by a factor of 2. So one step gave us 4 to the 1 and n over 2. Now we're getting 4 to the k of these things and n over 2 to the k, right? Now our elementary operations, these were operations on like 2 qubits, right? So what we need is to basically break this down to the level where we're going to demand that M is basically 2. If we demand that M is, sorry, I realize I'm getting cornered here, but if we demand that M is 2, what that implies, in fact, okay, I'm going to move a little bit over here just so this is visible. And also because I found Barenco's description of this to be sufficiently, so detailed that I couldn't extract anything from it. So, okay, here's the idea. CN knot breaks into 4 C M knots with M around n over 2. Do this more times, and you get 4 to the k times C M naught with M going as n over 2 to the k. So that means what we should do is we should set k going as log n, log base 2n. If we set k going as log base 2n, we get m order 1, which is what we wanted. That means elementary gate. Right? So once we're down to elementary gates, we only took this k steps, and the overall number of operations we've ended up with is 4 to the k times like C naught. And so that's just going to be like n. So it's going to be order n C naughts. Right? So we have this huge complicated operation. We break it down hierarchically, halving the number of control qubits at every step. And in the end, we find that this horrible operation can be implemented using a linear number of C naughts. Okay, so here are big complicated gates. Final step is to show, and I've detailed this in the notes. The final step is to show basically why this is all useful. So the point is basically, it goes in 2 steps. So what we need to do is construct these 2-level unitaries. Okay, so now from Cn naught to 2-level unitary, and then from this 2-level unitary we get any unitary. Okay, so okay, maybe in the interest of time, I'll just say, why should we do this? This is basically an important statement. So, but there's something you can look up very easily. Why should we do this? The point is that any u can be expressed in the following form. So this is like, imagine this is a D by D matrix. Any u can be expressed as a product over indices j and k, which run from like 1 to d. Sorry, it's leader science notation, from 0 to d minus 1, of operations that are called ujk. So this is a theorem. Any u can be written in this form for ujk with ujk of the following form. So ujk basically has if we write this as a matrix, then it has this property. So for basis states L but are not equal to j and k, these are the basis states defining our subspace, right? So this is just like a statement of a bit. This is j is a bit string, right? E.g., like j you can think of as like 0, 1, 1, 0, 1, 1, 0. So if L is not equal to j or k, then we act with the identity. So identity operation is just this. But then for L equal to j or k and L prime equal to j and k, then we have something non-trivial. Okay, so this you can actually see iteratively. It's not too tough. So the idea is basically what you do is you take your initial u, and then you imagine multiplying that big unitary by a matrix of this structure, but you choose this matrix in such a way that you eliminate some off-diagonal matrix element of the original unitary, okay? Then you just do this step by step. You keep multiplying these little unitaries and iteratively like deleting through the matrix product off-diagonal elements of u. This is, as I mentioned, detailed in the notes. So the point is that because of this theorem, given any big u, if we can implement these 2-level unitaries, we're done, okay? So we just need to know how to implement these 2-level unitaries using our multi-controlled CNOTs. Now, let me show you why it's plausible that you could do this. I'll give you an example of a 2-level unitary. Okay, so we want something to act non-trivial and just do basis states, right? So an example of a 2-level unitary is on n qubits, let's say, is just C n minus 1 u. Okay, this is a unitary acting on 1 qubit. And the point is that in this case, we freeze the states of all of the other qubits, and we just act with this unitary on the final qubit, right? So this thing acts non-trivially in only a 2-dimensional subspace. But the thing is, this is very special in that the two states entering the kind of non-trivial unitary here, the two basis states, they differ only in the bit value on one bit, right? So it's a two-level unitary for J and K here, for basis states that differ only in the location of one bit. So, for example, this could be, so this is UJK for J equal to 1, 1, 1, 1, dot, 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 1, 0, and K equals 1, 1, 1, 1, dot, 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 1, 1. Okay. So that's one two-level unitary. The point then is that more general two-level unitaries can be constructed from this operation and multi-controlled CNOTs. Okay. So that's one example. And the statement is that more general, again, this is described in the notes and also in detail in Nielsen and Chuang, reference in a moment. More generally, any two-level unitary from Cn minus 1 not plus swap operations and Cn minus 1 u. So the idea is pretty simple. So what you want, the idea is that imagine you have J and K that don't look like this, they're not so simple. The idea is you take your state J. Let's say it's some totally randomly arbitrary state, right? And then you imagine some path through the space of bit strings that turns it into K. Okay, we imagine some path through the space of bit strings where we flip one bit at a time. So for example, after one, we might change this bit here. This is some path through the space of bit strings. This is called a gray code. And you keep going on this path until you get to the end. And so the last step in this path would be, for example, maybe we just haven't flipped this last bit yet. So that would be the last step. Okay. The idea is you chart out these paths through the space of bit strings. They have no other end steps. The point is that you can use a Cn minus 1 not to kind of move for swap basis states. Okay. So you use these Cn minus 1 nots to kind of travel through this path through the space of bit strings. And then at the final step, you use Cn, you hit it with a Cn minus 1 u, and then you transform back. Okay. So you like walk through Hilbert space, apply this multi-controlled u, and then you walk back. And that gives you any two qubit unitary. So this deconstruction of unitaries into, yes, this deconstruction is described in some detail in Nielsen and Chuang. I'll put what I'll do is I'll put the reference on the Google form, where you can also find some other useful links. And then there's actually also a kind of, I found much more useful deconstruction of this in some handwritten notes from Professor Simon Fraser. So I can provide a link to that as well. But okay, that kind of brings us to the end of these two final steps, brings us to the end of the construction of a generic unitary in terms of local operations. Just to review, CNOT, which is a 2-qubit gate, and a single qubit unitary can be used to hierarchically construct multi-controlled NOT operations and multi-controlled U operations. Those multi-controlled U operations can be used to construct these two-level unitaries, and those two-level unitaries give you any generic unitary. Okay, so this was a very computer sciencey way of framing the problem, right? So here we were asking, if we have some like function or unitary in this case that we'd like to implement, how do we sort of convert that into assembly code, right? So this is one perspective on the kinds of unitaries you can implement. But you can see that what's going to happen is if I sort of pick a unitary U in advance, I'm going to end up finding, oh, I should stress here, this is like, there's like ordered d squared things here, right? And d is 2 to the n. So in general, a unitary, can be implemented in this way, but it takes enormous depth, right? So the computer sciencey way of thinking about it, I suppose, is you say, I have a function I want to implement. How do I build that? In the next lecture, we'll come to a complementary view on what you can implement by thinking about the kinds of the kind of evolution that is just implemented when you take a bunch of qubits and you start acting on them with gates, okay? And that's going to give us that's also going to give us a very nice way of understanding the breakdown of classical computation and when it is that quantum computers become necessary. So, okay, here, construction of generic unitary using quite complicated gates. Next time I take a qubit chain, I act with gates on it, and I'm going to ask when is it that the computation defined by the action of these gates runs beyond the classical computer. Last thing I'll comment on, in more in connection with what we were talking about today, and relevant to a question earlier about tridiagonal Hamiltonians. So another very popular universal gate set that people are working on quite a lot at the moment is the so-called Clifford plus T gate set. So Clifford plus T, it's kind of a neat decomposition. So the idea is that the Clifford operations, you can have a very simple operation on operators, right? So when you think about quantum mechanics in the Heisenberg picture, you don't evolve states, you evolve operators. The Clifford operations have their operation on operators can be efficiently simulated in the classical computer, right? So the idea is that Clifford only, classically simulable, and then the idea is you throw in this one extra 1 qubit gate called the T gate, and then it becomes non-simulable on the classical computer. So that's that framework is kind of nice because it also shows you that like the difference between classical computation and quantum computation is basically just parameterized by the number of these extra T gates you throw in. Again, there's just a sort of cursory description of this in the notes. But yeah, I recommend checking that out and also reading in more detail about these works on Clifford plus T. Again, I think I'll provide links to the relevant literature on the Google form. Okay, thank you for listening.
Thank you.
So that should be order of n squared, or is it that you just wanted polynomial scaling to exponential?
Could it be? So 4 to the log 2n. Yeah, should be, shouldn't it? So if I have, you see, okay, yeah, so it's k is going as log n, yeah, it's just polynomial, poly n. Yeah, sorry, just poly n.